Alright, so in this video we are going to prove that the dot product of our vectors u and v is equal to the magnitude of u times the magnitude of the projection of v onto u, right? So right here, what we're going to do is basically set up our definitions for these two sides with our vector u defined as ab in component form, and our vector v defined as cd in component form, right? Now right here we can basically sort of set up our two sides with these two component forms. Some of this is going to involve a little more work, and we'll talk about that in terms of the projection of u onto v, but for the most part it's going to be not too terrible to represent with these component forms. So right here, if we're talking about the dot product of our vector u and our vector v, we can say that that would be horizontal components, the product of horizontal components, so that's AC, plus the product of vertical components, so that's BD, right? And we're saying that that is going to equal the magnitude of u times the magnitude of the projection of u onto v. Now, magnitude of u isn't too tough to determine with our vectors a, b, and c, d. But the projection of u onto v is going to take a little more work, and we want to define our projection of u onto v. Oops, going to give ourselves some room here. We want to define our projection of u onto v, right, in component form. So right here what we're going to say is the projection of, v onto u, not u onto v, is going to basically be our dot product of u and v. So right here we're going to say the dot product of our vector u, which is a, b, and c, d, over, and then it's going to be the magnitude of u squared. So the magnitude of u is going to be the square root of a squared plus b squared, and then that quantity squared. So there's our scalar that we are going to multiply our vector u by. And our vector u, again, is right here, that a, b. So right here we can simplify the numerator a little bit, and then we're going to distribute that scalar, this big scalar, through to both a and b to get the projection of u onto v. So moving all this stuff down a little bit more, this is really most of the work. Right here what we're going to have is AC plus BD, there's our dot product, over, and then the square and the square root kind of cancel out, so we've got a squared plus b squared, and that's the scalar we're going to multiply our vector u by. So right here we will go ahead and distribute through that scalar to both the horizontal and the vertical components. So that's going to give us, right here, that scalar of AC plus BD over a squared plus b squared times a. And then right here we have a little more room, so we'll move all this stuff over one more time. And right here we would get that same scalar, AC plus BD over a squared plus b squared times b as the vertical component of our projection of u onto v. So now right here we're ready to set up this side. Magnitude of u, again, not that difficult to evaluate. The magnitude of u is going to be the horizontal component of a squared plus the vertical component of b squared, square rooted, and now times the magnitude of our projection of v onto u. So right here we've got horizontal component, which is AC plus BD over a squared plus b squared times a squared plus, now right here we've got our AC plus BD over a squared plus b squared times, times b squared. So again, basically, it's the same definition of magnitude as we had before. It's just the horizontal component squared plus the vertical component squared, and then we take the square root of all of that, and that's the magnitude. So right here, what I'm going to do is go ahead and pause the video at this point and let you guys try to work through the algebra. And what I would do to prove this is basically go from this side, show that our red side is going to equal our blue side. Basically simplify this this big guy down, right? This guy right here down, until we get AC plus BD. So go ahead and pause the video and we'll take a look at it in a second. Okay, so now looking at this, we can start by distributing the square through our parentheses. Since we're multiplying everything, we can distribute the square to our original horizontal and vertical components, and to the scalar we distributed in, and that's going to give us AC plus BD over A squared plus B squared squared times A squared, and the same thing times B squared, right? Now, right here, since this scalar squared is a factor of both terms here, we can factor it out and say that we've got that scalar squared right there times A squared plus B squared, right? Now, next step, we can distribute the square that we're raising that scalar to the numerator and denominator. And now we've got A squared plus B squared squared in the denominator. We're multiplying two A squareds plus B squareds, we're dividing two A squared plus B squareds and multiplying one. So right here we can cancel one of those A squared plus B squareds we're dividing by the A squared plus B squared we're multiplying by there, right? And now right here we're also multiplying two square roots, right? So that means that the square root of A squared plus B squared we've got right here, right, can actually be multiplied under one square root, right? And now what we have here is A squared plus B squared that we're multiplying by and dividing by, and these guys can also cancel out, and that leaves us with the square root of AC plus BD squared, which square and square root canceling out gives us AC plus BD, which is the dot product of AB and CD, which is our dot product of U and V. There's our proof. Right here, we didn't take too long. I think it's something that I'd like you guys to try your hand at. In general, what you can notice is we use the same strategy we used for the trig proofs. We worked from the more complicated side, right, and tried to get down to the simplified side. That's generally the strategy you want to take. But again, we're sort of using algebraic steps to show that one side equals the other side, and that's what we've done here. Okay, so end of the video. Good work looking at this, and we will, if you guys have any questions, we can talk about it in class.